Many theorems assert that a property holds for all elements in a domain, such as the integers or the real numbers. Although the precise statement of such theorems need to include a universal quantifier, the standard convention in mathematics is to omit it. For example, consider the statement: if x greater than y, where x and y are positive real numbers, then x square greater than y square, which really means to say that for all positive real numbers x and y, if x greater than y, then x square greater than y square. So, to prove a theorem of the form for all x, p of x implies q of x, our goal is to show that p of c implies q of c is true, where c is an arbitrary element of the domain, and then apply the universal generalization. Here, both universal generalization and the universal instantiation applied are implicit. They are not explicitly stated. Because of this, we now focus on the methods that show conditional statements are true. The methods can be classified into two major categories. The first category is direct proof and second category is indirect proofs. There are many types of indirect proofs. Let's see what a direct proof is. A direct proof of a conditional statement P implies Q is constructed when the first step is the assumption that P is true. The hypothesis is true, right? And we do some subsequent steps and reach at the conclusion that Q is true, right? From the assumption that P is true, we have to reach to the conclusion that Q is true, right? Then the subsequent steps can use axioms, definitions, or the previously proven theorems together with the rules of inference and all. So if we prove assuming the hypothesis is true and reaching to the conclusion that the conclusion is true, then we call that proof as a direct proof. Now let's see an example to illustrate how direct proof method works. Right, we are going to prove the theorem: if n is an odd integer, then n square is odd. Here we assume the hypothesis is true, that the n is an odd integer. We assume that n is an odd integer, right? Now, what it means to say that n is an odd integer? Now, we go to the definition of odd and even integer. The definition says that the integer n is even if there is an integer k such that n is 2 into k. And n is odd if there is an integer k such that n is equal to 2k plus 1. So our assumption was that n is an odd integer. Now then, which means that n equal to 2 into k plus 1 for some integer k, right? Now n is 2k plus 1. What is n square? N square is n into n, that is 2k plus 1 into 2k plus 1, which is 4k square plus 4k plus 1. And now we rewrite that statement as 2 into 2k square plus 2k plus 1, right? So this is of the format 2 into k dash plus 1, where k dash is 2k square plus 2k, right? So now we got n square as 2 into k dash plus 1, where k dash is an integer, right? Because k is an integer, k dash is also an integer. Now, which means that n square is also an odd integer. Now, and we assumed n is an odd integer and we reached at the step where n square is an odd integer, which means that P implies Q is true, or this conditional statement, if n is an odd integer then n square is odd, is true. Let's see another example. The statement is like, if m and n are both perfect squares, then n into m is also a perfect square. Okay, so now we have to assume that m and n are both perfect squares. That's how the direct proof works, right? We assume that m and n are both perfect squares. Now, what is a perfect square? A is a perfect square if a equal to b square for some integer b. Okay, so now we assume that m and n are both perfect squares, which means m is s square for some integer s and n is t square for some integer t, right? Now nm is t square into s square, which is also ts whole square. Now we claim that ts is an integer as t and s both are integers, right? Now we got that nm is ts whole square, where ts is an integer and hence nm is a perfect square, right? Now we go to a third example where it becomes more interesting. Let's see. The statement is, if n is an integer and 3n plus 2 is odd, then n is odd. So according to direct proof method, we assume that 3n plus 2 is odd, which means that 3n plus 2 is equal to 2k plus 1 for some integer k. Alright, So which means that we get 3n plus 1 equal to 2k. Okay, so we are stuck here, aren't we? Can we conclude that n is odd from what we have arrived at so far? Is it possible to get n is odd from this statement here? So seemingly there is no direct way to conclude so, and hence the direct proof fails here. All other proof methods which are not direct are called indirect proofs. So let's see the first type of indirect proof here. We see a proof by contraposition. Now, proof by contraposition is a proof method which works based on our equivalency that P implies Q is equivalent to not Q implies not P. Right? We have seen that a conditional statement and its contrapositive are equal. Right? So now we make use of this fact to build our proof by contraposition. So here we prove not Q implies not P is true instead of P implies Q. And we use the direct proof method to prove the statement not Q implies not P. So we assume that not Q is true and we'll do some steps, right? And we'll conclude that not P is true. And consider the same statement. If n is an integer and 3n plus 2 is odd, then n is odd, right? Now here P is 3n plus 2 is odd and Q is n is odd. Now we take the negation of both of the statements. Negation of Q is n is even and negation of P is 3n plus 2 is even. Now we are going to prove that if n is even, then 3n plus 2 is even, right? So now if n is even, we assume that n is even, right? Now we apply the direct proof method and we assume that n is even, which means that n equal to 2 into k for some integer k, right? And now 3n plus 2 will be 3 into 2k plus 2, which is 6k plus 2, and it is also 2 into 3k plus 1, and which is also 2 into k dash, where k dash is 3k plus 1, right? And k dash is an integer, and hence we get that 3n plus 2 is also even. This is how we prove using proof by contraposition. Alright, let's take another example. Now the statement here that we want to prove is if n equal to ab, where a and b are positive integers, then a is at most root n or b is at most root n. Now there is no obvious way of showing that a is at most root n or b is at most root n starting directly from the equation n equal to ab, right? And hence we attempt a proof by contraposition here. Now if n equal to ab, a is at most root n or b is at most root n is what we want to prove, right? Where P here is n equal to AB, Q here is A is at most root n or B is at most root n. Now if you consider the negation of Q, we apply the De Morgan's law here to get the negation of Q, right? Q is of the form A or B, R or S we can consider, and R or S, the negation of it is going to be not R and not S, right? According to De Morgan's law. So not Q will be A greater than N and B greater than N. Right? So we got that negation of Q is A greater than N and B greater than N, and negation of P will be N not equal to AB. And we are going to prove the statement not Q implies not P here, right? So we attempt to prove that if A is greater than root N and B is greater than root N, then N is not equal to AB, right? Alright, so if A is greater than root N and B is greater than root N, then A into B will become greater than root n into root n, which means AB is greater than n, and which definitely means that AB is not equal to n. And hence we prove the statement not Q implies not P, which means that P implies Q is true. Next type of proof method we are going to see are vacuous and trivial proof. Okay, so we consider the conditional statement P implies Q. Alright, so what will be the case when P is false? When P is false in a conditional statement P implies Q, we know that P implies Q is always true, right? So if we can show that the hypothesis is false in the conditional statement P implies Q, we can prove that P implies Q is true. And that's exactly the vacuous proof tries to do. And now what if we prove that the conclusion or the consequent is always true? So in a conditional statement P implies Q, what if we prove that Q is always true? which means that P implies Q is always true, right? And this is what trivial proof tries to do. And now we're gonna look at the famous proof by contradiction. So suppose we want to prove that a statement P is true. Alright, so now we want to prove that a statement P is true. So we assume that not P is true. That's how the contradiction proof works. We assume that the negation of the statement is true. Alright, and suppose that we arrive at a contradiction Q from our assumption, which means that not P implies Q is true, right? But Q is false. Because Q is false and not P implies Q is true, then it has to be the case that not P has to be false, or in other words, P has to be true. This is how the proof by contradiction works. Because the statement R and not R is a contradiction, where R is a proposition, we can prove that P is true if we can show that not P implies R and not R is true for some proposition R. Now, let's look at a classic example to illustrate how proof by contradiction works. Now, prove that root 2 is irrational using proof by contradiction. Alright, so the statement P is such that root 2 is irrational, right? The statement P is such that root 2 is irrational. Now, according to our proof by contradiction method, we assume that the negation of the statement is true. That is, we assume that root 2 is not irrational and root 2 is rational, right? So we assume root 2 is rational number. Now, what it means to say that a real number R is rational? So a real number R is rational if there exists integers P and Q with Q not equal to 0, such that we can write R as P by Q. Alright, now we also make use of the fact that every rational number can be written in its lowest term or in its simplest form. For example, 2 can be written as 4 by 2, but it can also be written in simplest form as 2 by 1, right? So since we assumed root 2 is rational number, we can write root 2 as a by b, where a and b are integers with b not equal to 0, and GCD of a comma b as 1, where a and b have no common factors, which means that a by b is written, root 2 is written in its simplest form. Alright, so now let's call this equation number 1. We square this equation number 1 to get 2 equal to a square by b square, right? And from this we get that a square equal to 2 into b square. Now according to the definition of an even number, a square is an even number here, right? Now we make use of the fact that if a square is an even integer, then a is also an even integer, right? So we are not proving it here. This can be proved using proof by contraposition. So why don't you guys try it out as an exercise? So anyway, but I am not gonna prove this fact here, and I'm gonna assume this fact, and from this we get to know that if a square is an even number, a is also an even number, right? So if a is an even number, a is equal to 2 into p, where p is some integer, right? Now we got a as an even number, which means that if we substitute in this equation a square equal to 2b square, we get 4p square equal to 2b square. From that we get b square equal to 2 into p square. From that we get that b square is an even number, right? And now we make use of this fact again to get that b is also an even number. And finally we get both a and b as even number. But we assume that a and b doesn't have any common factors other than 1. Or in other words, GCD of a comma b is 1. Now we get these two statements R and not R here, where R is that we can write this root 2 as a by b, where GCD of a comma b is 1. Negation R is we can write root 2 as a by b, where a and b are both even numbers. So R and not R happens from our assumption not P. R and not R is a contradiction, right? It's a false statement. So we got that not P implies R and not R. So this has to be true only when P has to be true, or in other words not P is false, right? And hence we get that P is true, which means that root 2 is irrational. Let's look at a conditional statement here, and we want to prove the statement using proof by contradiction. The statement is if 3n plus 2 is odd, then n is odd. Alright, So this is a conditional statement. So it is of the form P implies Q. So we want to assume the negation of the statement is true. So negation of P implies Q is nothing but P and not Q. So we have to assume that P and not Q is true. So here we are assuming that 3n plus 2 is odd and n is even, right? So but we know that if n is even, then 3n plus 2 is even. We have already seen this before, right? Now let's consider the whole conditional statement as statement S. We assume that negation of S is true, right? And from this assumption, negation of S, we go to the statement that where P and not P both are true. So negation of S implies P and not P, right? This is what we arrived at. But P and not P is a contradiction, right? And hence it means that our assumption was false, and hence the statement if 3n plus 2 is odd, then n is odd is true. Alright, so the next proof method is proof of equivalences. Now to prove a biconditional statement P if and only if Q is true, we need to show that both P implies Q is true and Q implies P is true. So here we got two conditional statements, both we want to prove as true, right? So we already know proof methods for conditional statements that we apply here to prove that P implies Q is true and Q implies P is true. Now the validity of this approach is based on the tautology P if and only if Q, if and only if P implies Q and Q implies P. So to show that n statements are biconditional, meaning that P1 if and only if P2, if and only if P3 and so on if and only if Pn is true, we need to show that P1 implies P2 is true and P2 implies P3 is true and so on, and Pn implies P1 is true. Again, this is based on the tautology P1 if and only if P2 if and only if P2 if and only if Pn, if and only if P1 implies P2 and P2 implies P3 and so on, and Pn implies P1.